have our two hypotheses. And for our first hypothesis, we will say, well, Yn is in the first hidden layer. And then we will perform the weight recovery individually using Xi. And then our second hypothesis will be, no, Yn is in the second layer. And then we will do the same. We will again perform the weight recovery individually. For both of those hypotheses, we will record the maximum absolute correlation value. And we will compare. And since the correlation depends on both the input to the multiplication operation, incorrect hypothesis will result in lower correlation. So very simple. We assume our neuron is first layer, our neuron is second layer. If our neuron is first layer, we have this. Our neuron, sorry, is in the second layer, we have this. Observe correlation. Better correlation means correct assumption. If our assumption says, well, this neuron belongs to the first layer, okay, I go to the second neuron, third neuron, fourth neuron, blah, 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 blah. At the moment when my neuron says, well, it's second layer, I know, okay, this was the boundary between layers. I continue, 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 third layer, continue, 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 all the way to the end. And then finally, once we have all the parts, y does not grow exponentially as the number of layers because so the effort does not grow exponentially with the number of layers because we attack every layer separately. So we are looking at every layer separately. And then when you do that, it just grows linearly. So the more layers I have, for sure more effort, but it's just linear. So we attack layer by layer. For each layer, we attack every weight separately again. And then the whole, you compare just two layers every time. Yes, exactly. We only always need to compare two layers because think of it, neuron can be either here or here. It cannot be there. So it's either, and if you start with the beginning of your neural network, you know it must be in the first layer or in the second layer. There is nothing else. Once you find the boundary, you know all the neurons after that need to be in the second layer or the third. You could have 7 neurons of 7 layers. Exactly. You would do the first neuron, and you would assume it's the first layer, and you would assume it's the second layer. And then your correlation would say it's the first layer. Then you would do the second neuron, and then for the second neuron, the answer would be, well, is it first layer? Is it second layer? No, the second neuron is in the second layer. I already know from now on, I do not care about the first layer. I just need to assume is it second layer or third layer. I never need to go back. So, well, I could assume my neuron is on layer 7, but since I always start at the beginning of neural network, there always needs to be something that is in the layer 1. You cannot jump to layer 7. It's sequential processing in your feed-forward network, so it goes from layer to layer. It cannot be processed on layer 7 before it's processed in previous layers. Is it clear? I presume then this would be name Elior. I talked about the case. It could be every neuron and every layer. Yes, but again, it's the same. Every neuron on every layer. So you want to say every layer has only a single neuron. No problem there. You just start with the first neuron, and you will get it's in the first layer. You go to the second neuron. You ask, is it first or second layer? You will get answer, it's second layer. You go to the third one, continue. Or if everything is stuck in one layer, you will do first neuron, is it first or second? First. Second neuron, again first. Third neuron, and you will come all the way to the end, and always your hypothesis will be correct that is in the first layer. If the algorithm runs parallel on GPU, can you assume that nodes manipulated together belong to the same layer? So this is a tricky question because that's why also we do not talk about GPUs, but on microcontrollers on devices like that, so that we do not need to assume everything that is happening on modern GPUs. But you could attack again modern GPUs because it's the same way modern GPUs also run AES, and you can attack that. So for algorithms like that, you commonly need more measurements, but also think of it. Parallel setting also can give you more information on some other parts. So while now it seems, okay, how would I know? Yes, but in parallel, some other parts to attack would be simpler. So you could attack GPU, of course. It would be more effort because simply GPU has not so good signal to noise ratio. That's why you would need more measurements, but you can attack. So how do we do that? Let me just show you graphically. So first, you do your acquisition, you do your CPA to obtain two hypotheses. So the layer-wise, for every neuron in the network, you would compare the correlation. On the basis after that, you would identify the activation functions, and you would reconstruct the network. It looks simple, but it's quite a lot of work to do attack like this. And when I say work, I mean time-wise. Depending on the size of the network, this can be, of course, a lot of effort. But what kind of result do we get if we actually think of a little bit more trickier targets? So already if you go for cortex, ARM cortex, you can see the differences between patterns for sigmoid and tan-H to be smaller. But again, the amplitude, the magnitude, so the value on the y-axis is different. So that's why you can still differentiate between. And this is how it actually looks like for devices like this. Here you can see the correlation, and you see that we need 500, 1,000 different operations running of the algorithm. So algorithm operations, let's say classifications, to be able for our correlation to tell us the difference between the correct and the wrong targeted value, so the weight. This is also to answer how many measurements do we need? Well, apparently here we would need at least 1,000 to get some kind of distinction. So if you do the attack, we attacked some simple data sets commonly used in the community, and we first measure the performance with the original neural network, and then we measure the performance with the neural network that we reverse engineered. And you can see the difference between what we reverse engineer and the original one is very small on second or third decimal place. That difference comes from the fact that from time, first of all, we rounded weights on 2 decimal places, and second, we do make mistakes. Luckily, not many mistakes, but whenever you make a mistake, it can make it worse. For MNIST, you can also see similar results. You can attack also more complicated architectures like convolutional neural networks, like someone asked in the beginning. It's just a little bit different data storage, so you need to be careful on that, but the attack still works. What is interesting to note here is look at the correlation and on the number of traces. So before, for instance, to attack MLP, we needed, let's say, 1,000, but here we need, well, depending what kind of scenario do we have, 10,000 or 100,000 measurements. So to reverse engineer convolutional neural network, we need quite a lot of measurements. It's a lot of effort in obtaining the measurements for this. When is the break? Now? Okay.